There's a really interesting question that emerges from all this research about how sunburns damage cells at the molecular level. Can this detailed scientific knowledge actually translate into better prevention in the real world? The answer, fortunately, is a resounding yes, and we're already seeing concrete examples of how cellular knowledge is improving skin cancer prevention in practical ways. First, understanding the specific molecular mechanisms of UV damage has enabled the development of more effective sunscreens. First-generation sunscreens simply blocked some UV radiation in a relatively nonspecific way. Modern sunscreens are designed based on precise knowledge of which wavelengths of UV radiation are most damaging to DNA and which chemical compounds can specifically absorb or reflect those wavelengths. We're also seeing the development of sunscreens that don't just block UV radiation, but also contain antioxidants that can neutralize the free radicals generated by the small amount of UV that inevitably penetrates, providing a second line of defense at the molecular level. This is sophisticated stuff based on deep understanding of cellular chemistry. Second, understanding the early molecular changes that occur after UV damage is leading to the development of early detection tools. Researchers are working on tests that can detect molecular markers of cumulative damage in skin, allowing identification of areas at high risk of developing cancer before any changes are visible. This could enable targeted preventive interventions, like topical treatments that stimulate DNA repair or that eliminate precancerous cells. Imagine being able to identify and treat problem areas before they become actual tumors. That's the promise here. Third, knowledge of the specific cellular mechanisms that lead from UV damage to cancer is informing new public education strategies. Instead of just saying, use sunscreen, public health messages can now explain exactly why it's important, connecting concrete actions to understandable biological processes. This more sophisticated education can be more effective at changing behaviors, especially among young people who might be skeptical of generic advice. When you understand what's actually happening at the cellular level, you're more likely to take protection seriously. Fourth, molecular research is leading to the development of what's called precision medicine for skin cancer. By understanding the specific mutations and molecular changes that characterize different types of skin cancer in different individuals, doctors can design personalized treatments that specifically target each tumor's molecular vulnerabilities. While this is more treatment than prevention, the line is blurring. Detecting and treating precancerous cells based on their molecular profile is essentially prevention at the cellular level. Fifth, and perhaps most exciting, therapies are emerging that can reverse some of the molecular damage caused by past sun exposure. There are compounds under investigation that can reactivate tumor suppressor genes that have been epigenetically silenced. There are enzymes that can repair specific types of DNA damage caused by UV radiation. While these therapies are still mostly experimental, they represent the promise that past damage doesn't have to be completely irreversible. The connection between basic science and practical application isn't always direct or fast, but in the case of skin cancer, we're seeing relatively effective translation of molecular knowledge into real prevention tools. This gives us reasons to be optimistic. The more we understand about what happens at the cellular level after sun exposure, the better equipped we are to prevent the long-term consequences and protect people effectively.